So let's get to the last part of our lesson, which is to talk about Laplace transforms using math. Now, the text, as always, I think does a great job with the math part, but I'll describe it too. Okay, so f of t is your time domain equation, that e to the minus 2t u of t example, and then f of s is your Laplace transform. In the S domain, also called the frequency domain. And this 0 minus thing down here, that just means a time just before 0, which if it has certain unusual spikes at 0, it matters. For most equations, it doesn't. It's just the same thing as 0. So when you take differential equations, they talk about Laplace transforms, you're going to spend a lot of time, at least a week, maybe half a month, talking about if the Laplace transform exists. They'll talk about whether or not this integral converges, because it's true that for certain f of t's, the integral won't converge. Here's the great thing. And the Mitra text, the text you'll read also talks a lot about it. The math text talks a lot about it. The great thing about us in electrical engineering is that if f of t exists in the real world, then the Laplace transform exists. So in math classes, they'll have equations like this, and they'll show that there is no corresponding f of s for this input equation. We don't worry about that because this doesn't exist in the real world. That goes up to infinity, and it goes up to infinity really fast. If an equation has a finite energy so that you can actually create it, the Laplace transform exists. The integral converges. I'm going to give you an example, but just before I give that example, I want to give an aside, a math aside. It's a review, really. So recall that u of t looks like this. So as an example then, we can do tricks, and we can say 6 u of t minus 2. And Aiden, I don't think have I called on you yet?
No, sir, you've not.
Fantastic. Tell me about what 6 u of t minus 2 looks like. Where does it go up?
So it will go up at x equals 2.
That's right.
And it will go up to 6.
That's it. And again, it goes up at x equals 2, at t equals 2, because when t equals 2, the argument to u is 0, and everything interesting happens when the argument to u is 0. All right, now armed with that, let's do an example, and then our lesson will be over. You need to be able to work these by hand. That's being able to work Laplace transforms by hand using this integral definition is the purpose of this first lesson. Let's say you're given this function, e to the minus at, where a could be anything, u of t. The question is find f of s. When I was an undergraduate, I was really curious about what this S meant. And I know I already told you, don't worry about it, don't think about it. If you're really curious, S is actually not even a real variable. S is a complex variable, and it's got imaginary parts and real parts. And so it transforms this function that is a one-dimensional line in two-dimensional space into f of s, which now exists along the complex plane. So now it's a two-dimensional surface in three-dimensional space covering the complex plane. That's why I'm saying don't worry about what the intuition is. And it doesn't, and you don't need to know it for what we're talking about. Instead, to find what f of s is, you just plug it into our equation. So we'll plug it in and get e to the minus at u of t, e to the minus st dt. All right, so that's already looking pretty nasty. Now I'm going to tell you Squire's law, because I'm just that narcissistic, of integration. And the rule is, if you have anything with u of t's, first get rid of the u of t's. That's the whole law. So we need to get rid of this u of t. How can we, I forgot the little minus there. How can we get rid of that? Let's, when I don't know how to do something, I draw it. So I'm going to first draw what that part looks like. What everything other than the u of t looks like. So here's my picture of what e to the minus at, e to the minus st looks like. And man, didn't I just even tell you that st is a complex number? So I've got no idea what that looks like, you know, something crazy like that. All right, well, that's not very helpful. But when we multiply it by our u of t, all of a sudden, what we see is that it's going to be, it just zeroes out everything less than 0. And then whatever is greater than 0, it continues on as if it wasn't changed. Does that make sense? Thumbs up? Okay. So in other words, armed with that, we can now continue on our solution by saying, for time, we're going to integrate this and find the area. Well, if we were going to integrate everything, it would be like this. But we were actually only interested in the integral greater than 0 to begin with. So we were only ever interested in that area. Well, that's the same as this area. So in other words, we really haven't done anything. We can just get rid of that entirely. And we have the same result. Now, notice how different that is than if we had something like, we want to take the integral from 0 to infinity of e to the minus at times u of t minus 3, e to the minus st dt. Can you see for now, you can't just ignore that u, because now for this one, it's doing this. And this is the new area that we need to integrate. So for that, we need to change it from 3 to infinity of e to the minus at, e to the minus st dt. Thumbs up on that? How it's different there? Awesome. How about this one? And who haven't I talked to yet? Yeah, Jonathan, I'm looking at you. If instead of it being yeah, I am talking to you. My wife is from the Bronx. She's a sweet little girl, but holy cow. She's got that "you talking to me" thing down. All right, so what if instead we had the u of t plus 3? In other words, now, Jonathan, where does that one turn on?
I would left shift it so you'd go from negative to infinity.
That would be, so now it looks something like, this. But where do we want to integrate? Where do we want to start to integrate that?
We still want to start at 0, don't we?
We still want to start at 0 because this equation, the equation says you're only going to do it from 0. So it's going to be the integral from 0 to infinity of e to the minus at, e to the minus st, dt. Yep, correct. Good, great. All right, so now let's just finish this up. What happens? Who are we having left? Preston, what happens when you multiply two exponentials? What is the rule?
You add the exponents.
Yeah, add them. T, dt. So it's that. And when you integrate, what do you do to an exponential?
You take the exponent down. Wait. Yeah.
So is it minus s? I need a little bit more room. So you're saying it's minus s plus a,
and then leave the rest the same.
e to the minus s plus a t, and we're going to integrate that between 0 and infinity. That's almost it. Ben, do you want to fix the one problem? I can't hear you, Ben, so I'm going to ask again, Preston. Oh, yeah, go on.
Could it be 1 over the negative s plus a?
Yeah, that's it. And the reason to see that is, Preston, if you try to take the derivative of this, can you see how this would come down? Now you'd have squared, s plus a squared.
Yeah, I can see that.
So the integral would have to do this. So now if you took the derivative, it would undo that. So that's the integral. And now we can plug in the numbers. So let's do that. We've got, there's no t down here, so that just pops out. And now we've got e to the minus infinity, and we subtract that from e to the 0. Okay, given that, who else do I have in the class? I think I've called on everyone. Joe, what's e to the minus infinity?
Isn't that 0?
Yeah, and there'll be 0. Here's an example. This is e to the minus 2t. So if we just carried it out into infinity, it'll be totally 0. And Joe, just keeping on with you, what's e to the 0?
That'd be 1.
1. So this whole thing just becomes -1, which takes away that minus sign, and so the whole thing becomes s plus a, and that's your answer. And it's a good thing we kept it as a, because now you can plug in anything that you want to for a. You found a general rule that'll work for all kinds of transforms. And just to check with what we did at the very beginning of class, we said that this is just this with a equals 2. And sure enough, this is our answer with a equals 2. And in a math class, you'd have to talk about regions of convergences for S, and we don't worry about that because if it's a real signal, it exists. Okay. That was a lot of stuff. Any questions about it?